So far, we've discussed the F statistic at a conceptual, non-mathematical level, and how it's calculated by dividing the variance between our groups by the variance within the groups. To actually calculate an F statistic, we use a process called partitioning the sum of squares. In this video, we'll lay some of the mathematical foundation for how and why we do this, which we'll then continue with in our next video. But first, I need to point something out so you don't get confused later on. In introductory statistics, we've been using X as our generic term for whatever the variable is that we're interested in. We've had X bar for the group mean and X sub I for a person's score on whatever variable it is that we're looking at. But now we're going to change the letter that we use. And instead of X, we're going to start using Y. Now, nothing else has really changed. We're just moving from using X to using Y. So instead of something like X sub I being a person's score for an assessment or a health measure, it will now be Y sub I. And instead of X bar being the mean on some variable, it will now be Y bar. But other than using the 25th letter instead of the 24th letter, nothing has really changed. So why use Y? Well, without getting technical, ANOVA reflects a transition to advanced analyses that can involve multiple variables all at the same time. And when we do that, Y is used as the outcome variable and X is used for different predictor variables that we'll use. Now, you'll see this in advanced stats courses like EHD 574. So I want to introduce the notation now for consistency then, all right? But again, we're just using Y instead of X. Nothing else has changed, all right? So let's get back to calculating our F statistic. Now, this process is a little complicated, so it may help to work backwards a bit, starting with the F. Right? Now, we previously saw that F is equal to the variance between groups divided by the variance within groups. But how do we calculate a between groups variance and a within groups variance? To do that, let's take one more step backwards and ask ourselves, what's the generic formula for calculating the variance? Now remember, variances are equal to the sum of squares divided by the degrees of freedom. But now we have two different types of variance, so we'll need to use two different types of sums of squares and two different degrees of freedom. We're going to have a sum of squares and degrees of freedom that's between the groups, and a sum of squares and degrees of freedom that's within the groups. All right? Now, to streamline the language a bit, we'll refer to these as just the sum of squares and degrees of freedom between, and the sum of squares and degrees of freedom within. So, kind of putting all this together, we'll use the sum of squares between and the degrees of freedom between to calculate the variance between, and we'll use the sum of squares within and the degrees of freedom within to calculate the variance within. And then we're going to use the variance between and the variance within to calculate our F. All right? But again, how do you calculate the sum of squares between and the sum of squares within? And to accomplish that is where we get to use this very cool thing called partitioning the sum of squares. Now, to understand what that involves, think back to when we first learned about the sum of squares. Let's say I'm interested in how students do on a history exam. To calculate the sum of squares, I would get a sample of students who took the exam. I'd calculate the mean score on the history exam for all of them. Then I'd calculate the deviation score for each person from that mean, and I'd square all of those deviation scores, and then I'd add up all of those square deviation scores, right? And that would give me the sum of squares. And in this case, the sum of squares would be that measure of the total variability in our history exam scores, right? Sum of squares describes that total variability in whatever variable we're looking at. But now let's imagine that we have the exact same data with the exact same students, but now I recognize that the students reflect several different groups who receive different curricula. Some use one curriculum, others used a different curriculum, and others use some other curriculum. It's the same sample with the same scores. The scores are just as spread out as they were before. There's just as much variability. Nothing's changed. So the sum of squares for the history scores hasn't changed at all. It's still going to be the same sum of squares when we look at everybody. But what if I notice that the scores for some curricula are generally high, and the scores for students in another group getting a different curricula are all kind of low? Again, nobody's scores have changed. The overall sum of squares hasn't changed one bit. I've just noticed that some of that variability is related to the curriculum group that students are in. Can I figure out how much of that total variability, how much of that sum of squares is related to those group differences? Now, it's important to remember that the total variability, that sum of squares we started with, has not changed. It's exactly the same as it was at the start. The scores haven't changed. It's just that now I see that those scores are also reflecting group differences. Can I somehow tease apart the piece of that total variability, that part of the original sums of squares that's related to those group differences? Right? That's where we're headed. But to get there, it helps if we first break each student's score into 3 different parts. All right? Let's do that by keep working with this same history example. All right? Now, specifically, let's say that I want to compare several different groups of students who receive different history curricula. All right? And our outcome measure is the scores on the history exam, right? We'll assume that the scores range from 0 to 100, with an average score across all of the participants in all of the groups equal to 75. We're going to call that the grand mean. Again, it's the average across everybody in all the groups. All right? Now, we'll say that one of the groups receives the Roman rules curriculum, and the mean for that group is 85. And finally, there's Theo, a specific student in the Roman rules group, and he performs a little better than average for that group, and he scores a 90. Now, reflecting this, you can think of any individual student's score as being the sum of these 3 different pieces. The grand mean, right? Plus the difference between their group mean and the grand mean, plus the difference between their individual score and the group mean. To illustrate that, let's take a look at Theo's score. Right? Theo scored a 90, we saw that. So this is the sum of the grand mean, which was 75, plus the difference between the group mean, which was 85, and the grand mean of 75. So 85 minus 75 is 10, right? plus the difference between Theo's score of 90 and his group mean of 85, which is 90 minus 85, or 5. We add these up and we get 75 plus 10 plus 5, or 90, which was Theo's score, right? See that? We've broken it into 3 different parts. Now, let's take a look at that visually. And at the same time, I want to introduce some new notation. So let's start with our possible range of scores from 0 up to 100, right? We know Theo scored a 90, which is right around here, okay? Now, the grand mean, again, the mean for all the scores across all the groups, was 75. So if we shade in the area below 75, this reflects that portion of Theo's grade, his score, that is reflected in the grand mean. Now, because we have means for each group and the overall grand mean, we're going to use y double bar, 2 bars on top, to indicate the grand mean. That just helps us keep track of whether we're talking about a group mean or the grand mean. Now next, we know the mean for Theo's group, Roman's rules, was 85. Let's shade in the area between the group mean and the grand mean, all right? Now, mathematically, we can write that as y bar minus y double bar, the group mean minus the grand mean, or 85 minus 75 is 10, which again is the difference between Theo's group mean and the grand mean, right? Then there's the difference between Theo himself, his score of 90, and the mean for everyone in his group. That's 5 points, right? Mathematically, we write that as y sub I, Theo's score, right, the score for person I, minus y bar, or the mean for his group, right? 90 minus 85 gives us 5. Great. So if we put all that together, we see that, again, Theo's score is equal to 75 plus 10 plus 5, which still gives us 90. All right? Now, of course, the same principle works for everybody's score. So let's mathematically write out someone's score based on these 3 different components. We have y sub I. Again, that's just a way of saying the outcome score for person I is equal to the grand mean, y double bar, right? Plus the difference between their group mean and the grand mean, y bar minus y double bar, plus the difference between their individual score and their group mean, y sub I minus y bar. Okay? Now, let's stop here for now. In our next video, we'll take this insight, how we can break scores into 3 pieces reflecting the grand mean and differences between group means and the grand mean and differences between individuals and their group mean. And we'll use that to calculate our sum of squares between and the sum of squares within. All right? Take care. Bye-bye for now.